the Permian is the biggest mass extinction by far, way bigger than the one that wiped out the dinosaurs. And these old mass extinctions, you have to just chemically and climatically make the world so horrible that complex life can't live on most of it. What they found was that one of the biggest series of volcanic eruptions ever, this thing called the Siberian Traps, erupted and magma intruded into the crust that it could have covered the lower 48 United States in a kilometer deep of this stuff. It's actually not the lava and stuff that's killing everything. It's all the gases that are coming out of the volcanoes. And CO2 is the second most abundant gas that comes out of volcanoes. But on the way up, these volcanoes would have been burning through ancient natural gas and coal deposits and limestone. So they would have been acting like industrial civilization, just like to an insane degree. Like if we burnt all our fossil fuels and then we just kept burning, limestone for fun for centuries for some reason, like then you can finally get into the realm of the Permian.
A warm welcome back to Decouple. Today I'm joined by returning guest, Peter Brannen. He's an award-winning science journalist and contributing writer for The Atlantic. He wears a number of other hats at research institutions, but he's widely celebrated for his, I will say, deeply researched books on Earth history and climate. We had you on, Peter, I believe about a year ago, to discuss The Ends of the World, which explores the planet's great mass extinctions, which are also the basis of its great hydrocarbon deposits. So lots of interest amongst all the energy geeks that listen to this podcast. But today we're having you back for a new book. You've got them coming fast and furious. And this is the title, The Story of CO2 is the Story of Everything. And it really is a vast piece of storytelling. I'm started chipping away at this book several weeks ago, and I'm still chipping, I will confess. And that's why we're going to break this interview into two and follow along this fascinating tale. So first off, welcome back. It's good to have you here.
Yeah, thanks so much for having me back. I'm excited to talk about this book. You said they're coming fast and furious, but this took about 5 years to pull off. So it's good to be able to talk about it.
Yeah, I mean, there's some good language. I mean, the language is really rich. It's beyond the subject matter. You're good wordsmith, Mr. Brannen. But one of the terms in there that struck me, I'll see here. Like there's a term of humanity being this obligate pyrophile. I thought that was really smart, and sort of we're Homo sapiens, but we're also kind of like Homo ignis, like igneous rocks burning, Homo pyrus, the pyromaniac ape. I don't know which. But we're this like incredible dissipator of energy that the planet has sort of tied up in these disequilibriums, which we're going to get into today, which are, the story of the carbon cycle. And we dissipate energy on par with hurricanes and orders of magnitude more than volcanoes as your book unravels. So there's a lot to sort of lay out there in terms of exploring, the book's called The Story of CO2 is the story of everything. I mean, the story is also the story of reduced carbon. And so carbon's the basis of life. We got a lot to talk about today. But I guess first off, carbon is a trace element on Earth. What stoked your interest? 93% of the Earth is like iron and magnesium and silicon and oxygen. Why this measly carbon? Why do you care?
I mean, that stuff is also very interesting. Maybe that'll be my next book. The Story of Magnesium is the story of everything. But no, I mean, it sort of naturally spun out of my first book, where the punchline of that sort of was that you might be familiar with mass extinctions as these things that happen when rocks fall out of the sky and kill all the dinosaurs and stuff like that. But having followed the geoscience community closely, I recognized that the conversation had sort of changed, where actually in the last few decades, when paleontologists had gone out to these bigger, even older mass extinctions looking for evidence of an asteroid, they didn't find it. And instead they found these weird sort of geochemical events that were intrinsic to the workings of the Earth itself. These tectonic things, sometimes including these major mind-bending, continent-spanning volcanoes that put tons of CO2 into the air over thousands of years and probably made it warmer than we ever even could. But it was sort of, it was this interesting experimental record in the Earth's past of like, what happens if you run the sort of experiment we're running as an industrial civilization today, and you just keep going down that path basically as far as you can. And amazingly, there is this experimental record in the Earth's past that shows us just how gnarly things can get. And in the worst case, they cause the biggest mass extinctions ever. So that book was kind of about how CO2 is this big scary thing, in the same way that it's often presented in the news. It's this, thing that when it goes up too fast and in too big of quantities, it causes warming and all these problems that we're worried about on the planet today. But in the course of writing that book, coming from the geoscience world and the earth science world, there's a much bigger story. There's a much bigger context for what this thing is. And I just felt like that hadn't really pierced the public imagination. And, it really is. And I don't think it's overstating it to say that the behavior of this thing, CO2, and as it moves between these reservoirs of CO2 and organic carbon and back to CO2, and things like carbonates and limestones and things like that, it really is what makes Earth, the behavior of this thing on the planet. Because there's this thing called the carbon cycle, which is in normal times in Earth history. It's all sort of very finely imbalanced. CO2 is coming out of volcanoes, which is a very good thing because life on Earth is carbon-based, and the source of that carbon is CO2. So we need CO2 or there wouldn't be photosynthesis and everything would die. It also maintains a habitable temperature for the planet. Like if you took all the CO2 out of the air right now, the temperature would drop by like 60 degrees Fahrenheit or 35 degrees C in a half century, and you'd go back into the Snowball Earth and you'd kill everything in that way. So it's good that this stuff is in the air, and it's kind of miraculous how amazingly balanced it is normally as it comes out of the crust and then into the oceans and the air and through life and then back into the crust. So I just wanted to kind of pull back and give more context for people of what this thing is and its role on this planet and the fact that it makes Earth, Earth.
Yeah. So I do want to do a tour of deep geologic time, because I think what we're going to talk about today in terms of how I've outlaid it, and I'm willing to riff and flow in all sorts of different cool directions. But I think the superstructure is really going to be walking through deep Earth time, getting us up to the Pleistocene, where, again, Homo sapiens emerges, and later on Homo ignis or Homo pyrus or pyromaniac human emerges, because that's another whole important section of the book that we just won't have time to get to today. But this is fascinating. Before, like, I want to get into a time-traveling machine. And as improbable as it is, we'll probably put on a breathing apparatus, because I think for about 4 billion years of Earth history, like there's no oxygen, just going to asphyxiate or some other horrible, it'd be like mustard gas. I'm not sure what.
Yeah.
But I guess before we get there, I just wanted to, we just briefly talked about the carbon cycle. I think that's good. We're going to get into it in far more detail, but volcanoes outgassing, rocks reabsorbing, and now photosynthesis and, respiration or burning. But just this idea again of, CO2 is the story of everything, but we mentioned reduced carbon. Now, I actually didn't have to write my MCAT, my medical college admission test, because I went to a really weird hippie school in Canada, and I was all ready to deep dive organic chemistry, but I didn't quite get there. So I had to resuscitate some basic chemistry just to get this all sorted out. But again, in terms of like carbon serving as this incredible battery, energetically, and humans sort of being in between this disequilibrium of all this, hydrocarbon or carbons plus hydrogens, and then this flammable atmosphere, and reuniting the two. Just for a second, if we can just get into that idea of sort of this like redox chemistry to just get our heads around that. And we don't have to go into deep detail because but I thought it'd be interesting to set that up, because beyond, life being carbon based, this important source of energy that we're harnessing to have this conversation right now, just if we can do a little bit of basic chemistry for a second.
Yeah. Well, I mean, there's this handy, I guess learning tool in geochemistry where it's actually the words oil rig, where its oxidation is leaving. It's an electron leaving. If something's oxidized, it loses an electron, and rig, reduction, is gaining. So it's gaining an electron. And usually, sometimes electrons and hydrogen are kind of used interchangeably in biochemistry. So the trick that life pulled off, it's very difficult to reduce CO2 on our world. To add hydrogens, insert them into CO2. It's very difficult. It takes a lot of energy. It's not, especially in a world with oxygen, it would just rather react with oxygen and go back to water and CO2 rather than being organic matter. But plants pull off this miraculous trick by harnessing photons from the sun. And, photosynthesis is an absolute miracle, but it's only they can only pull this trick off with the energy of the sun, which temporarily they jam some hydrogens into some CO2s, and they make plant matter, which is this energetic stuff that then, because it's out of equilibrium, the rest of us can eat it and burn it with oxygen back to CO2 and water and release that energy to power our lives. But the early Earth, there wasn't any oxygen on the planet. And so, you had to somehow, the first life had to figure out a way how to make organic matter abiotically, which is very difficult to do. If we could do that today, we wouldn't be digging up fossil fuels and burning them because, we could just make this reaction happen very easily on the surface. So we live off, the largesse of this ancient plant life, which did this trick for us, making these energetic organic compounds. But the earliest life isn't any oxygen on the planet, and it's actually very hard to make organic carbon, like I was saying. And so I talked to these origin of life researchers who put the origin of life not at the, Darwin's warm little pond on, up on the surface on land, because the more we learn about the early Earth, it seems like there probably wasn't much land at all. The oceans might have been twice as deep, and the surface of the planet was a horrible place to be. There were insane UV radiation and hurricanes around the clock, and the planet was just a really unpleasant place. But you would have had these hydrothermal vents at the bottom of the ocean, and not the ones that most people are familiar with, the really violent ones, but these very gentle things called alkaline hydrothermal vents that amazingly just sort of abiotically make a lot of the compounds kind of at the basis of metabolic activity for all life on Earth. They just kind of do it for free. And especially in the early Earth, it would have been reducing CO2 with hydrogen would have been this natural thing that happened at these interfaces between this, still very reduced ocean crust and an ocean that was filled with CO2 and was acidic. And these things really would have wanted to react. And there would be these metal catalysts at these vents that could force that reaction to happen. And what is incredible about the chemistry of these vents is it almost exactly reproduces the electrochemistry that happens in a lot of our cells today. That is this like miraculous out of equilibrium thing that people struggle to come up with ways how could this impossible intricate machinery that powers all the cells ever have evolved. And the fact that it kind of resembles this geological structure sort of indicates, at least some people think, that maybe there's this transition from geology to biology where you're carrying out these reactions abiotically and then slowly life eventually bubbles off the vents, and then things like DNA and RNA become important and like channeling life and things like that. But so that's a very broad global view of
I love it because I was fascinated by origin of life experiments, the famous sort of lightning in a bottle experiment. But as you mentioned in the book, like that is a sort of one-time burst of energy. It doesn't seem like I had a child in a neonatal intensive care unit for a while. Like the kind of, for life to get going, it needs something that's calm and smooth. And yes, there needs to be some disequilibrium energy gradients, but like we got to nurture something pretty fragile. And then I discovered Robert Hazen's work recently. I think, I forget what institute he's with, but he talks about, the way that the clay and minerals actually create these sort of proto-cell membranes through which you can get these proton gradients, which you're discussing. And I guess these vents are basically just spitting hydrogen out, spitting protons out. And so you get, the fundamental mechanism for life dependent on this energy source. But then later, life is able to create its own cell membranes and mimic these early sort of clay mineral layers, make its own phospholipid layers, internalize a reducing environment, and free itself from. But so it's so elegant, as you were mentioning.
It's actually the hydrogen that would be coming out of these vents would be like free hydrogen. So it wouldn't be like protons alone. It's actually the electrons from the hydrogen that would be important here. And there'd be a lot of protons in the ocean because it would have been really acidic. So it's this unique environment that carries out those reactions for free. But I mean, you coming from a medical background, for me, this book was really a deep dive. I knew the geoscience stuff. The human history stuff was kind of jumping in the deep end for me. But learning the miraculous nanomachinery of a cell just makes me so grateful to even be alive for like 10 seconds without falling apart. So that was sort of the mind-blowing thing for me is learning, I learned it in high school biology, but for some reason it didn't click. How miraculous the electron transport chain is, pumping protons to one side of a membrane and then being let back down to power a turbine that makes ATP to send it off. I mean, it's insane stuff. And I also had this sort of like stoner moment where I realized that is basically pumped hydropower storage.
Yes, pumped storage, baby. Yeah. Maybe I literally read it in your book, but it did feel like, and I think that's the great thing about this book is you have all kinds of moments where you feel brilliant because you think that you thought it up. That is very cool. So, okay, so we've kind of got that there again, life is carbon chains. We're a carbon-based life form, and abiotically, in the right environment with enough hydrogen, and the right metal catalysts, as you're mentioning, you can get oxygen to piss off and turn into water, and you can start creating some methane or even some carbon chains. So I think we've got that down. I now want to time travel a little bit, and it is always kind of a little bit intimidating to try and get one's head around like how different the Earth has been. We've been on the planet. We've been keeping a historical record for 4,000 or 5,000 years. There's a lot of time behind us, and the planet looked nothing like it did today. So this book, again, I've been sort of nerding out on the stuff and deep diving it, but you did an amazing job evoking these different eons even. And so I'd like us to kind of hop in a time machine and go to the Hadean. Tell us a little bit about what the planet looks, how big the moon is, what's going on with the tides, and what's happening in terms of that carbon cycle. Because I think what's missing will help illustrate, as we progress through geologic time, what we start to see in terms of, more and more interactions in terms of how this carbon cycle works.
In the Hadean, it's what the sort of the crazy world I was mentioning, where it's really deep oceans and no ozone layer, and this the moon would have been much closer,
like crazy close, right? Like what is it, 10
pretty
times
close?
closer?
Yeah, I'm not sure the exact numbers, but it would have been a full moon would have been pretty spectacular in the Hadean. But as you were mentioning, there's no oxygen. The oceans would have been, completely toxic. Even if you were given like a scuba stuff and you went in the oceans, I'm pretty sure you'd die pretty quickly. Because it's, there's just all this horrible stuff in it. But then over billions of years, you start getting the formations of continents, which emerge pretty meekly from the ocean and then slowly consolidate. And the more land you get, exposed to weather, the more you can draw down CO2. So where Venus might have gone off on this escape route into the greenhouse hellhole, the Earth might have been saved by the fact that you had these emerging continents that managed to help bury down CO2 and keep it at a temperate climate, I guess. But still, you don't have any oxygen. Even there's this thing called the Great Oxidation Event, which I think is sort of misleadingly titled, at least in the ways that it's often presented in the popular press, where I think people think like, oh, then you get oxygen and then you're off to the races.
Yeah, then we could breathe or something.
The growing consensus now is this thing that happened 2.5 billion years ago. It does dramatically change the fossil record because like minerals that you can't get in a no oxygen world do suddenly show up at the Great Oxidation Event. So it is this break in Earth history geologically for sure. But I think people have this impression that, you could, and then there's oxygen, and here we are. But I think sort of we think it might have gone up to like 2% of the atmosphere at best, maybe. And then it seems like that happened for a couple 100 million years, and then it crashed again potentially, and stayed very low for almost 1 billion years after that. And it's sort of this eerie fact of geological history that photosynthesis might have evolved over 3 billion years ago. But you really don't get a planet that we would consider breathable until only the last few 100 million years, which sounds like a long time, but that's like the last 10% of Earth history. So there's this mystery of why the planet had photosynthesis and had sources of oxygen, but stayed stubbornly low oxygen, and potentially animal life stayed, the champagne cork stayed on the champagne bottle of animals until very late in its history when oxygen suddenly rises.
And so, like, people talk about the Fermi paradox and, the universe is so vast. Why have we not been contacted yet or made contact with intelligent life out there? And, it's interesting. So many things had to go exactly right, and we could deep dive a list that's probably 100 of entries long. But even just when the carbon cycle was more one way and there was just kind of outgassing and no rock weathering in the Hadean, we needed all that CO2 because the sun was very dim, right? And so, wow, that miracle happened. And then, you talk about the Great Oxidation Event, and it just feels like this little blip in terms of, obviously, as you mentioned, it changes the chemistry, the banded iron formations. There's lots of oxygen sinks that kind of absorb it. But you talk about this boring billion. And that's a long ass time. And I think that's what you're basically describing. Photosynthesis has started and just not much is happening. I think in your book, you say like life's great accomplishment at this point was basically just creating a slimy ocean or like massive algae.
there's people who study this period, also known as the Mesoproterozoic, that would get mad about the characterization of it as the boring billion, because there is some stuff that happens. There's the origin of eukaryotes, which is like monumental, but it, you know, multicellular animal life still is like very far in the future. And so you get these very, very simple riffs on multicellularity, you know, some kinds of seaweeds and stuff. But if you went to this world, oxygen would still be incredibly low. And yeah, the most interesting thing that you'd see from sort of a animal biased perspective is pond scum. That's sort of life's great accomplishment over its first 4 billion years or so. So yeah, it's an alien world for a lot longer than we would, I think most people appreciate. And it really isn't until the age of animal life, some 550 million years ago or so, that things start looking a little more recognizable.
You know, I had Professor Andy Knoll on a little while ago, and we were deep diving and talking about a few of the sort of elemental cycles. We did touch on carbon, but more nitrogen, phosphorus, and other things. And like, there's this, I'm not sure if it's a paradox, but there's this really bizarre moment with the Cambrian explosion where we basically have, you know, multicellular, you know, some unicellular life and maybe a few little creatures, as you're mentioning, and then all of it explodes into, you know, animal life and predator-prey relationships, and the Cambrian explosion, seas full of trilobites and all kinds of weird, you know, extraterrestrial-looking creatures, and you know, a lot of that has to do with, you know, basically the soup getting the ingredients it needs, the nutrients that it needs. But oxygen is a big one. And this is a key part of your book. You mentioned, we don't get, you know, get oxygenation events. Sure. These microorganisms are making oxygen. But it's just getting sunk. You don't actually get an atmosphere rich in oxygen unless you start making fossil fuels. Can you go into that?
Yeah. So this is really one of the more, counterintuitive revelations from geology that I think most people don't appreciate, which is that, you know, you see these, you know, no shade on them, but, you know, like conservation nonprofits will be like, oh, the next 2 out of your next 3 breaths are from plankton in the oceans, or 20% is from the Amazon today. And that's not really true. That's not really why we have an abundance of oxygen on the planet today. It is true that plants and plankton make a lot of oxygen, but not nearly enough to account for how much is in the air. And the reason why Earth has such a massive abundance of oxygen is that if you're, say, like a tree and you make oxygen in your lifetime, and then you fall over and you die and you get eaten by fungi and beetles, and, you know, your energy and your carbon goes back into the forest, eventually that's all turned back to CO2 by aerobic respiration, by everything else that's living in your ecosystem. And it's kind of a wash. Just as much oxygen is consumed as is created. And so in that environment, you get a world with about zero oxygen, not this crazy surplus of 21% of this gas that wants to react with everything and really doesn't even want to be on the surface of the planet. And the only way to get that surplus is if you imagine this same tree, it dies, and instead of getting eaten by the rest of life and, you know, turned back to CO2 and water, that tree is quickly buried in sediment and eventually becomes part of the crust. And the oxygen it made in its life isn't used up in its own consumption. It stays up, it's shielded, and stays up in the atmosphere. And if you then think this happens to enough trees and plankton blooms over all of Earth history, this infinitesimal little leak of carbon into the crust, you're slowly accumulating this huge surplus of oxygen in the air. So we don't often think that the reason why you can breathe is because there's fossil fuels under your feet, but that is kind of that is the reason why you can breathe. Like fossil fuels in quotes, because we call them that when organic carbon in the crust is economically exploitable. But most of this stuff is not. It's diffuse enough in mudstones and things that we're not ever going to like wipe out oxygen by burning fossil fuels. But it's just an interesting sort of flip of like how to think about why you can breathe.
Okay, and what truly is the great oxygenation event? I mean, it doesn't happen without photosynthesis, but to bury that stuff, you need sediments. And this is something that I find fascinating. Obviously, the Earth, it was all igneous rock. Like we have, 3 rock types: igneous, sedimentary, metamorphic. It was all igneous to begin with because it was all this big molten piece of lava. And in terms of, again, Robert Hazen's work, I just love the guy talks about mineral evolution. But again, that composition, how the planet has changed over time from one big ball of kind of lava to sediments. And your book, I think, really opened my eyes on this. You can't bury that carbon without a bunch of sediment lying around. So let's talk about some dramatic swings in Earth climate that maybe enabled that. I'm not sure if that's like proven theory or not, but if it hit it, Snowball Earth.
It's definitely an interesting. I pursue some pretty interesting new ideas while flagging what the sort of older ideas are in the book. But there was this one that just blew my mind that I decided to follow. But I talk about this. Another sort of curiosity of the rock record of Earth history is that you do have this, 4 billion year preamble to the age of animal life. And right before animal life explodes in the fossil record, you get the greatest climate catastrophe in all of Earth history, this thing called Snowball Earth, which lasts tens of millions of years, which, early climate model people would see pop up in their climate models, and they just disbelieved it because they thought there's no way the Earth was ever glaciated all the way to the tropics, because that would have killed all life and we wouldn't be having a conversation about it. But they did see that once ice sheets advanced to, I think it's like 30 degrees north and south of the equator, there's this feedback loop where it takes over the whole planet and freezes everything to death. And so they just dismissed this as a weird thing about their models. But then geologists started finding evidence for ice in the tropics at sea level around 700 million years ago, right before, on geological timescales, right before the age of animal life. And so, it is now, well accepted that there is this incredible spasm of glaciation, where the leading theory for why it happened is that CO2 might have been declining because of things like basalts weathering on the Earth's surface. So this is one of the techniques that, accelerated rock weathering for geoengineers. They want to artificially drive this process where you just inject CO2 into rocks and it turns them into things like limestone. This also happens naturally, and this is one of the, if I'm getting too far down the weeds, let me know.
No. I want to go right into the middle of the weed patch here.
It might have been for reasons that I explained in the book why that might have been especially active in the lead up to Snowball Earth. And suddenly you pass this threshold where CO2 drops enough, ice sheets advance enough, and the whole planet freezes. It goes in and out of that glaciation at least twice. And the escape route that the climate modelers didn't really foresee was that if you encase the entire planet in ice, you're shutting down all photosynthesis and you're shutting down all rock weathering. So you're not burying any CO2 anywhere on the planet while the planet's encased in ice. But all along you have these volcanoes that are poking up above the ice, and they're just steadily putting the stuff into the air. So you're adding it over geological time spans and not removing any of it. And suddenly you can reach this threshold on the other direction, which might have been insane. It might have been like 100,000 parts per million of CO2. So today we're worried about it being 420. This is like 100,000. And, overnight, geologically, the whole thing melts catastrophically, and suddenly the ocean is covered in a mile-deep lid of 120-degree water, and it's this super greenhouse that's hotter than the Earth's ever been. And you go in and out of this a couple times, and then
back into a full snowball again.
Yeah, suddenly in the aftermath of that, you are the ice sheets have ground the rocks into flour, and then it's super hot and there's tons of weather. So that's an incredibly good way to weather rocks under that environment.
More surface area, more CO2 combined. So
and all this phosphorus is weathering in off the land, which is firing up these huge algae blooms, which are another good carbon, are good at burying carbon as well. So then you plummet back into the snowball, and then you rocket out of it again after 15 million years, and then things calm down for a little bit, and then all of a sudden the fossil record is littered with these big, weird, strange animals at the dawn of large, complex life. So it's this crazy story, and people, there's this ongoing debate there must be some relationship between these two things happening. What were they? I explore kind of a crazy one in my book, but I think the sort of traditional explanation is that the oceans might have been starved of phosphorus for a long time, and when you start weathering out of the rocks in a modern sort of tectonic regime, suddenly life has enough, that's often the limiting nutrient in oceans today are things like phosphorus and iron and stuff. So that might have propelled life. But as you said, people have talked about the Cambrian explosion being related to the rise in oxygen. And I described this previous mechanism for driving up oxygen, which is burying carbon in the crust. But in order to bury carbon in the crust, you need to build up the rock record, which we kind of take for granted that there is a big there's strata, everywhere we look, and there's a fossil record. But it seems like in the boring billion, there wasn't much being built up, or maybe it was all destroyed during Snowball Earth, because you get this crazy thing called the Great Unconformity.
And is this where the one-armed man is rafting the Colorado River?
Oh yeah, John Wesley Powell.
And then he sees this, like, basically there's this big missing chunk of the rock record.
Yeah, in the Grand Canyon. This guy John Wesley Powell in the 19th century sort of
like, we're all nerds here. We're up for this. So,
yeah,
so
okay,
I want you to go
cool.
Deeper.
Yeah, there is this weird feature of the rock record all around the planet, and everywhere, most places we've looked, where up to sometimes beyond 1 billion years seems to be missing from right before the age of animal life, this thing called the Great Unconformity. And the weird idea I explore in the book is that in order to build a rock record, you needed to destroy a lot first, so that you can go into this growth regime where you are suddenly stacking up rocks and filling them with carbon and injecting oxygen into the air. And one idea is that Snowball Earth might have caused the Great Unconformity. Just the glaciers would have just been these, plows that would have scraped off, the average in one paper says like 3 to 5 kilometers off the face of the Earth, off every continent, which is just mind-blowing. Or the Great Unconformity is the product of the really weird tectonics during the Boring Billion, where you had this supercontinent that overstayed its welcome and things were just sort of worn down. But whatever it is, something changed, because after then you get this record of life where the guy I talked to, Shannon Peters, thinks the fact that a lot of rocks are missing is why you can breathe, because if they hadn't been destroyed, then you wouldn't have built up this, he describes as a capacitor, where you are oxygenating the surface of the planet by filling its crust with all this carbon. So that is, there's a reason why everything we've talked about so far takes about 250 pages or something to describe. So I hope it was legible.
It's so cool. It's so cool. And if you just think about it mechanistically, like if you wanted to bury a bunch of life, if you had a big forest growing and you wanted to bury it with igneous rocks, like lava on top, you just burn it and you'd return all of that painstakingly fixed organic carbon to the atmosphere. So you need sediments. And as we were saying, like as you move through time, like I think, in terms of like evolutionary biology or dogma has taught us, like there's no progress, like evolution has no goals. Life might get more complex and it might get simpler just as it more adapts to the environment. But we do have these progress narratives in terms of like there's more and more and more sedimentary rock as Earth gets older. And that just kind of makes sense. I've got, more, I don't know. I'm thinking about being sedimentary myself as I get older. I'm sedentary and little bits of me are falling off. But also, life just consumes more and more energy. There's a few sort of things which we can definitely see, kind of progress in. But this, I live in former glacier country, right? Like in Ontario here. My dad was sort of vehemently anti-American United Empire loyalist who, was always annoyed that so much good fertile soil got scraped down into the U.S. and we were just left with a bunch of gravel and sand. But suffice it to say, you needed that sediment to bury that carbon. And that is the Great Oxygenation Event. At least that is one of the theses that you explore. I think it's hella compelling and a really interesting narrative.
It's the second Great Oxidation, because I mentioned this earlier one that was like 2.5 billion years ago, but then that one kind of flounders out potentially. What's spooky about this guy, and I should like sort of signpost that, again, this is sort of an unusual explanation for why or how Earth was oxygenated. I'd say the standard one is just that geochemical cycling just sort of changed at the dawn of animal life, and we don't have to worry about it because we're on this like we now have a modern world and we don't have to worry about oxygen. But his model is like far more freakish and contingent, where you needed this sort of cataclysm to enable us to breathe. And then, he has these real speculative ideas that, well, the first oxygenation event didn't last forever, and maybe this one won't either. So when he was really going out on a limb, but so yeah, it's a cool idea. But as you were saying, yeah, there's this expectation in textbooks that the further back you go, if the rocks were just getting created and destroyed on sort of the textbook way, you would see exponentially less as you go back in time. But instead what you see is this one-off massive jump in sedimentary rock right at the age of animal life. So it's interesting.
Okay, so some cool stuff's happening. You mentioned that supercontinents are kind of a dangerous time for life. And again, just to finish our Snowball Earth chapter of this episode, just curious if you can talk about, we're familiar with how the continents are arranged now. Some of us have heard of Pangaea. Rodinia was the supercontinent before that. And I think this guy referencing, he talks about how Rodinia and having a supercontinent could, play into one of these big climate perturbations. Still mediated by CO2 in large part, but also there's other factors at play. So I don't know if we can talk about Rodinia for a little bit.
Sure. There's sort of a very brief supercontinent called Pannotia that I don't really talk about in the book. But yeah, the big ones are Pangaea and Rodinia. At least those are the last two big ones. But Rodinia, Pangaea was sort of this big, sort of crescent-shaped thing that went from pole to pole in the, near the beginning of the age of dinosaurs. But Rodinia is a 500 million years before that. So this is like unthinkably ancient. And the geography is just totally scrambled. It's not worth trying to make sense of like where things are on the planet, because I can't even remember it. But in the book, I'm talking about East Antarctica being to the west of, North America and stuff. It doesn't make any sense. But it might have been dangerous because unlike Pangaea, which sort of was pole to pole, some reconstructions have Rodinia sort of just being this blob along the equator. So most of the sunlight hits the mid latitudes, and if you just have land there, it would have been reflecting a lot of it back to space. And then even worse, if you start to have CO2 decline and ice sheets form on the poles, they're not covering up any land, which is bad, because if you shield land, you stop it from weathering, which buries CO2, but you're not doing that. So CO2 just keeps declining as the ice sheets advance on the world. And then once they reach this, once they reach Rodinia, they are, it's too late because they've already gone far enough on the planet. And then this ice albedo feedback kicks in, and you drop into Snowball Earth. But yeah, it might have been preceded in the initial stages of Rodinia breaking up, because you had all these huge basalt flows all over Rodinia as it was in the process of breaking up. And as the supercontinent started to fracture, you would have started getting weather in there, which would have been drawing down CO2 as well. So there are all sorts of things that are specific to the paleogeography and lithology of Rodinia that might have primed the planet for a snowball. But it seems like it's weird that at the next supercontinent, which I write out in the book, Pangaea, is also not a good time for life, but for the opposite reason. It gets incredibly hot. So it seems like supercontinents are bad times on Earth, and we're lucky that the next one isn't supposed to come for about 250 million years.
Okay. So moving through time, we are starting to bury a lot of fossil fuels. We've talked about the sediments. Tectonics also super important, and I guess these shifting continents kind of infers that. But you need plates to be moving as well to subduct things. Why don't we move on now to the last, I guess, 500 million years, the Phanerozoic. This is kind of the Cambrian explosion. Life goes completely bonkers. We did, talk fairly extensively about the mass extinctions in our last interview together, and people should go back and check that out. But I do think it's worth revisiting, the Carboniferous, for instance. This is, and maybe some of these mass extinctions, which again are sort of the great era of our hydrocarbon deposits. You think about the Permian Basin. It coincided with the Permian mass extinction, right? So let's talk a little bit about these great moments of, burying reduced carbon, reduced organic carbon.
Yeah, so one that I really kind of linger on in the book is the Great Age of Coal, the Carboniferous, which aptly named Carboniferous, which it's sort of it's about 315 million years ago into early 290s or so. It's the Carboniferous into the early Permian really is the Great Age of Coal. And it's kind of bizarre that 90% of our coal deposits on Earth are from about 2% of its history. It's this weird little window. But to situate people in time, this is still a very alien world. And the Carboniferous, sort of the height of Carboniferous around 310 million years ago, you're still tens of millions of years before the evolution of dinosaurs. And this is, as I say in the book, I think if I had a time machine, it's the place I would least want to go back in all of Earth history, because it's the age of coal, so lots of carbon's going into the ground, and the flip side of that is that there's lots of oxygen in the air. So today it's at 21%. It might have gone up to 35% in the Carboniferous, which fueled the metabolism of these gigantic insects everywhere. So you had dragonflies the size of seagulls, and centipedes the size of alligators, and scorpions the size of golden retrievers. So it's this terrifying insect world, and it's also where all our coal's from. And those two things are oddly related because of that oxygen carbon link I was talking about. But yeah, so I spent time in Appalachia and got a tour with a local geologist at Appalachian State College and toured some coal mines. And it was just mind blowing to me. And I can't put myself in the mind of, a miner in 1910. You're holding your oil lamp, looking at the ceiling, and there's these bizarre, tree bark and fern impressions everywhere. And actually, one of the leading causes, or maybe not leading, but a recurring cause of death in the mines was actually these literal tree falls from these petrified trees would just fall out of the ceiling. They're called kettle bottoms there, but people were getting killed by tree falls from these 315 million year old trees. So it's mind blowing how our time period and this time period intersect. The planet, it's weird that so much coal comes from this one period in time, and there's a lot of theories for why that might be. One is that the fungi that can break down trees and things hadn't evolved yet, because it's actually very difficult to break down trees. Trees are these incredible, you look at the chemical structure of lignin, and it's just impossibly complicated, and it probably would be hard to eat. That theory is kind of in decline, and now it just seems like it was a unique tectonic thing where the pieces of Pangea were starting to assemble. So you're getting these big mountains on Earth in the tropics that cause these big subsiding foreland basins that would have had these swamps going from Kansas to Kazakhstan, as one geologist says. And then you also have you are going in and out of these ice ages like we have been in the last 2.5 million years, but this is 300 million years ago. So the sea level is going up and down over this time period. So you're not only having these thick swamps, but then you're suddenly covering them in sediment, and then sea level will fall again. You'll get these thick swamps. So that's where you get that bar-coded kind of effect from the coal layers in the age of coal. And so it might have just been sort of more a tectonic thing than a biological thing, but that's where most of our coal comes from.
So that's the Carboniferous. Why don't we touch a little bit on the Permian mass extinction again? You write very compellingly about extinction, and some of the stuff that stuck out to me was just, the Earth has been through a lot of stresses, and I guess Snowball Earth was kind of, it almost extincted life on Earth, but there wasn't that much complex life around. It's probably a lot harder to study. But there's been a lot of paroxysms of climate, of geology, volcanoes. And we really haven't had that many mass extinctions. And so, if like cheetahs, if 99.93% of the population dies, but a few survive, then that species makes it through. So these are kind of truly, truly extraordinary cataclysmic events. And the famous one, I guess you mentioned before, was when the dinos got smoked by the asteroid. And I guess geologists thought, well, all the extinctions must have been caused by that. And let's talk Permian. Let's talk about what happened there.
Yeah, the Permian is the biggest mass extinction by far, way bigger than the one that wiped out the dinosaurs. It is, the estimate's 90% of life in the ocean and 75% on land went extinct, which, as you're saying, it's very hard to wipe out a species. As I say in the book, like a pandemic, that if a pandemic killed 50% of human beings, it would be one of the biggest catastrophes of all time, obviously. It would be an unthinkable cataclysm. It would have absolutely nothing to do with a mass extinction, because A, you didn't drive this species extinct, and B, that's just one species on a planet with 8 million or whatever it is. So it's really hard to drive 90% of life on Earth extinct, especially without things like hunting and overfishing, and because that's most of the pressure on the environment today. Climate change and ocean acidification are these growing and looming threats, but so far most of the damage we've done has just been direct interference with the environment. And these old mass extinctions, you have to just chemically and climatically make the world so horrible that complex life can't live on most of it. And the most extreme version is the end Permian mass extinction, which is less familiar to people than the one that killed the dinosaurs. But you do have sort of a modern ecosystem on land. You have these big, ugly reptiles, and these things that are closer from our side of the family tree that are sort of the dominant terrestrial predators, things called gorgonopsids, and this whole weird branch of synapsids that are ruling the world. And in the oceans, you have, sponge reefs, and there's trilobites still, and sea scorpions still, and ammonoids, and, things that would look like nautiluses and stuff like that. And 97% of the ammonoids go extinct, and all the trilobites disappear, and all the sea scorpions disappear. And you can go to fossil sites, and it's hard to find a fossil for millions of years afterwards. And it seems like the planet was incredibly unpleasant for millions of years afterwards. And so obviously people wanted to know what happened. And given that there isn't convincing evidence for an asteroid impact, what they found was that one of the biggest series of volcanic eruptions ever, this thing called the Siberian Traps, that was they dated the lava flows and the magma intrusions to exactly at the age of the extinction, and enough lava erupted and magma intruded into the crust that it could have covered the lower 48 United States in a kilometer deep of this stuff. So I think I probably threw that stat out last time, but it just doesn't fail to amaze each time I say it to myself, because Yellowstone, it puts some ash on a few neighboring states, and it would be very bad if it rained the next day because it would just cause cement on people's roofs and stuff like that, and it would be bad for agriculture, but it has nothing on the Siberian Traps. But luckily, things like the Siberian Traps happen once every 100, 200 million years. And it was you'd think, okay, it's crazy there's that much volcanic activity, but it's actually not the lava and stuff that's killing everything. It's all the gases that are coming out of the volcanoes. And CO2 is the second most abundant gas that comes out of volcanoes anyways. But on the way up, these volcanoes would have been burning through ancient natural gas and coal deposits and limestone. So they would have been acting like industrial civilization, just like to an insane degree. Like if we burnt all our fossil fuels and then we just kept burning, limestone for fun for centuries for some reason, like then you can finally get into the realm of the Permian. And so you're injecting tens of thousands of gigatons of CO2 into the air. Temperature goes up something like 10 degrees C. We know that from both like geochemical proxies and by modeling work. So we're pretty confident in that number. And the ocean loses a lot of its oxygen because when CO2 reacts with, when it gets warmer, it just holds less oxygen to begin with. It acidifies, all this horrible stuff. And so that seems like a pretty convincing kill mechanism. But Pangea even makes things worse because, as I was saying, supercontinents it seems like the Earth system's kind of gummed up when you get into a supercontinent. And for Pangea, you would have had this vast arid interior where there's not much rain or weather reaching it. And so these normal breaks on CO2, natural CO2 emissions just weren't there because there's no rocks getting weathered in the middle of the continent. And just a simple matter of geography, there's less places offshore for, reefs and things like that. And so the planet can't really handle much excess CO2 to begin with in a supercontinent, much less this like world-ending volcanic eruption. And that's why it was so horrible. And Pangea suffers something like 6 or 7 other major and minor mass extinctions that are all related to, similar kill mechanisms, just because it had lost control of its, ability to regulate carbon dioxide.
Just really could not absorb well. And I'm blanking on kind of the follow-up to that, but I think there was several geologists that were saying, hey, things could never be as bad or get as bad because we have better carbon sequestration, obviously not human-induced, but just better geologic mechanisms now. Could you expand on that a little bit? That seemed like a slightly comforting moment in the book. It
might be that, we are in a lot safer world than the Permian to begin with. We're at a much better starting state. We're not in a supercontinent. We have these very disparate continents. There's been these biological innovations that have remade the carbon cycle in the interval. So right after the Permian in the Triassic, you evolve calcifying phytoplankton, which is kind of amazing. That didn't exist before until the Triassic, which is pretty late in the age of animal life. But that.
And this is just like shrimps with shells. Is that what we're saying?
No, it's like things like coccolithophores and phytoplankton. So it's like primary producers in the ocean that then zooplankton and things eat off of. But so you'll see satellite imagery today of some eddy in the ocean. It'll be this like blue-green thing, and a lot of that is things like this that are building calcium carbonate shells and photosynthesizing. And when they die, they fall through the ocean, and they have carpeted the seafloor in this like pavement of limestone, basically limestone ooze on continental shelves. That helps in bad times in Earth history, because when CO2 increases too fast, the oceans acidify, but when they turn over, if they dissolve this sort of layer of basically tums on the bottom of the ocean, it helps neutralize kind of how bad the event gets. And this didn't exist in the Permian either. So we have all these differences in our world than this nightmare during Pangea, but we're also injecting CO2 into the air at something like 10 times as fast as those volcanoes were. So even though they put much more into the air and it made it much hotter, that was over thousands of years. And I guess the scary thing about what we're doing now is there really isn't there's no good analog, even compared to those events, just in terms of how hard we're pushing the system and
how fast.
Yeah, and as I've said, like the carbon cycle is this very complicated thing that we don't fully understand. So we should be a little humble about how hard we push on it.
Yeah, to the degree that as a superorganism, we really have much in the way of free will over it. we'll see how that all rolls out. Yeah, it's just again like something as dull and boring as rock weathering being, how we soak up the CO2 and how relevant you're mentioning the position of the continents are. I guess we're going to move more into sort of more modern history into our current, or at least the geologic era, the Pleistocene, in which humanity emerges. Really weird time with extraordinarily low levels of CO2. In terms of the rock weathering, I understand one of the reasons is the Himalayas, have this uplift in a tropical area where there's lots of rain, and that's relevant. Like if the Himalayas had emerged, I guess, way far up north, it wouldn't have had the same climate impact.
Yeah, that's the sort of classic explanation. So I kind of just hand wave away the entire age of dinosaurs in my book because, it's right. The animals are
everyone talks about that.
The animals are very exciting, and there's lots of books about them. But from an Earth system perspective, not that it's kind of just a pleasant, warm place for a while. There's a couple crises, but they're not as bad as the big mass extinctions. So then the dinosaurs get wiped out, and the mammals sort of inherit this very warm greenhouse from the age of dinosaurs. And over the last 50 million years, we've declined from this sort of leftover greenhouse of the dinosaurs into what you were mentioning is what in geological history is actually surprisingly a very low CO2 cold world that you really have to go all the way back to the Carboniferous to find an analog to it. So to get from the greenhouse to this icehouse world that we are still temporarily in for the time being, because one of the, Antarctica has a mile thick ice sheet on it, which is, in Earth history, you don't really see glaciated continents that often. The Earth has been a greenhouse more often. But to get from that greenhouse world into our icehouse world, you need to bury CO2 somehow. And the classic explanation is that the collision of India into Asia pushed up the Himalayas, which weathered a lot of rocks, and even encouraged sort of the monsoon seasons, which, increases the precipitation to wear down those rocks. That has become a more contentious thing in recent years, mostly because the kinds of rocks that are in the Himalayas might not be that good at weathering rock. So there's alternate explanations is that in the past few tens of millions of years, it's been more Indonesia and that chain of islands because they're very made of this very weatherable mafic rock, and they're in the, getting covered in jungles and punished by precipitation. So they're helping draw it down. Subduction, the length of just like subduction zones all over the planet like changes over geologic time, and there might just be less outgassing of CO2 over the last 50 million years for sort of much longer term subtle reasons. So all these things contributed. We know that CO2 has been declining, and we know it's been getting colder because we have very reliable proxies for both those things over the last 50 million years. And then suddenly, around 2.5 million years ago, you start plunging in and out of these crazy ice ages. Depending on how you count, we've been in and out of dozens of glaciations and then interglacials like today, which are these brief warmer periods, where suddenly the CO2 blanket had like shrunk enough that these otherwise changes in sunlight at high latitudes in the summers that really weren't relevant when CO2 is high enough and the planet's warm enough. But now you get to start initiating these ice sheets there. And depending on the orbit of the planet and the way it wobbles in the solar system, you get more or less sunlight at high latitudes during the summer. And when you have low sunlight at high latitudes in the summer, you allow year after year growth of these ice sheets. So when we've been in that configuration, it's encouraged the advance of these really deep ice ages, like the one that ended a few thousand years, 20,000 years or 12,000 years ago, where at its height, sea level was 400 feet lower, and there was an Antarctica's worth of ice on North America, and it was a dusty, shrubby world. There was I think a quarter less vegetation on the planet. So our ancestors lived through all this stuff and these crazy jumps in and out of these ice ages. And we didn't survive these crazy climate changes in our recent prehistory because we have big fangs or thick fur or anything like that. It's because I would say two things that are related. We are, as you mentioned at the beginning, almost uniquely this fire creature on Earth. which is reflected in our anatomy. So, we have outsourced a lot of our digestion to the fact that we have this external metabolism where we use fire to, if you eat, you eat something, you don't have to just sit there all day chewing on it and then digesting it. Most of that work is already done for us by cooking it and by using tools and grinding seeds and stuff like that. We have externalized a lot of our metabolism, which has allowed us to invest in these huge brains that then unlock things like sociality and social learning and culture and technology. And that long-term climate change, you suddenly, like right around 200 or 2.5 million years ago, when you start plunging into these deep ice ages, is when our genus like shows up on the planet, the like Homo, and starts doing weird things like butchering animals with tools. There is tool use before this, but we do sort of seem like this new phenomenon on the planet. And during these really cold and crazy climate snaps in the Pleistocene in the last 2.5 million years, sometimes you do see these sort of divergences in our lineage and signs of increased tool use or culture, things like that, do often line up with these crazy climate snaps. And yeah, I think that is what allowed us to both survive what has been a cold, low CO2 world, and eventually, in this weirdly stable interglacial climate we've had for the past few thousand years, has allowed us now in happier times to just explode all over the planet in ways that is comparable only to a couple events in all of geological history. So that's the general story.
So, it's such a long Earth history, but I guess we're saying there's sort of three moments where we've had really low CO2 as we particularly had, the origin of Homo sapiens 200,000 years ago. And that would be Snowball Earth. That would be the Carboniferous and kind of the last 20,000 years, 100,000 years.
I could think of a few. I mean, there's a really ancient Snowball Earth that is associated with the first great oxidation event. So that's like 2.5 billion years ago.
Okay. So as to say, this seems like this is rare. This is unusual.
Very rare.
And the dinosaurs, like people, like I look at the dinosaurs and I'm like, God damn, you guys stuck around for like 150 million years, like super successful. Humans are probably going to be a little flash in the pan in terms of the longevity of our species, just because of just basic metabolism, I think, if you want to really abstract it. But part of that had to do with this extremely stable climate that the dinosaurs lived under. I mean, things were changing, supercontinents were forming and things like that, but 1,000 parts per million CO2 for quite a while.
Yeah, I mean, it was something around in that ballpark. It was a very kind of warm, stable world with a few exceptions. But yeah, we've really lived in a kind of crazy climate. And both us and all other life on Earth today are evolved for this low CO2 ice age climate. So people have made this argument that huge baleen whales today, they have these huge fat stores that has allowed them to find, shifting food sources over huge distances as we go in and out of these ice ages. I've said, we're in this weirdly low CO2 corner of Earth history. So who cares if CO2 gets higher? Like, it's been a lot higher in Earth history. But because the whole planet is evolved for this, the last few million years, to suddenly impose this alien greenhouse from tens of millions of years ago in a matter of centuries, life can bend, but it can also break. And that seems like such a huge jump. It's a big ask. Yeah.
Hey, alligators, you mind just, marching on your little pathetic legs, 5,000 kilometers north. But yeah, let's talk about that though. The Paleo-Eocene thermal maximum. We're reaching back a little further in history now. But people talk about the Permian as sort of the nightmare case, the RCP 8.5 trajectory maybe of, again, this just as an aside astounds me because these what do you call them again? Not the Deccan Flats, but
Deccan Traps. Yeah.
The Deccan Traps, this enormous, and these are not volcanoes erupting like little, cones, but just lava spilling out over vast territories, and really just burning, not just releasing, carbon from deep inside the earth, but burning through coal, burning through gas, burning through limestone, as you said, really unselectively. Like humanity, we have to go out and find the economically recoverable fossil fuels, right. And we're still so goddamn good at that that we're doing it faster than this process, which covered the continental U.S. in a mile high of lava. It's pretty extraordinary. But yeah, the other period that people sort of look back to is the Paleo-Eocene thermal maximum. And can you just describe that for us? How high CO2 got then? And really, that was not a mass extinction. Life. There's probably some stress, but life did pretty well, despite a pretty rapid change, I think.
fairly rapid. So this is very early in the age of animals. Age of mammals. Sorry, dinosaurs get wiped out 66 million years ago, and then this is 56 million years ago. And yeah, so this greenhouse climate is left over. It's a very warm world to start with. It's about 12 degrees C warmer than it is today. Just that's the starting point, and then it seems like over 20,000 years, about as much CO2 went into the air as recoverable fossil fuels. And the temperature went up 5, 6, 7 degrees more than it already was. And so this is an extreme warming event. It does take place over 20,000 years, and it takes 200,000 years for the planet to recover, which one of the first things that actually, as an aside, blew my mind and got me down this wormhole over a decade ago, writing about sort of this deep time perspective on climate change was this. I saw this sediment core taken from the North Atlantic Ocean that was went from sort of chalky, limey stuff, and then it went to red clays for, a little bit, and then back to the chalky, limey stuff. And the red clays that's like a 200,000 year span. And it's the Paleocene-Eocene thermal maximum when the CO2 acidified the oceans. And like I was saying, it dissolves this blanket of carbonates at the bottom of the sea. And that shows you the recovery period. And it's sort of humbling to think, whatever we do to the climate, it might leave a similar legacy. But it's only, it's a few meters of clay at the bottom of the ocean. And then the planet sort of gets on its merry way again. But that sort of, for me, was the first time I thought about this stuff, and it kind of blew my mind. But
so our skyscrapers will be ground to dust, but humanity may earn itself a little 6 meters of red clay.
Yeah. Oh, but it is something of paleontologists have wondered, why wasn't this a mass extinction? This seems like a major warming event. And instead, things do go extinct. There's this ocean acidification event. Reefs seem like they take a huge hit. But it's more known as this sort of lightning strike to evolution and diversification, because right after this, you get a lot of the first instances of all the modern mammal groups that, we're familiar with, or suddenly show up on the planet or diversify at this boundary. You see mass migration of animals all over the planet, so you shake things up a lot. So it is this transformative event. But it doesn't kill everything. And that might be because you do have this handbrake at the bottom of the ocean that's helping, stem the misery. And it also is over 20,000 years. So it's about the same degree of temperature change as we could induce, but it happens to such a different world, and it happens over a long time span. So this is sort of what I'm saying again, where it's like we study these things as analogs just because they're the best things we have in the fossil record. But in very important ways, they're not really analogous. So we draw what lessons we can out of them.
And so at that time, we have like crocodiles swimming around the poles and like tropical forests. And what about the tropics themselves? Like, how does the Earth warm sort of differentially?
During this warming spasm, the tropics might have gotten to just inimically hot for most animal life. It might have been really, really unpleasant there. But you do see, I went to Wyoming with some paleontologists, and you see it suddenly shift from what was already a jungly world to this like dry jungle for 200,000 years and then back again. And you see evidence of these massive storms and things and weather getting shaken up in all these crazy ways, but eventually the planet settles. But it stays very hot for a while. And yeah, you mentioned the sort of Arctic forests and stuff. In Canada, in Ellesmere Island, as far north as you can get, I talked to this paleontologist who goes there and studies these ancient rainforests that you can still see these tree stumps just sort of like eroding out of the tundra looking over the Arctic Ocean. And they're from this period 50 million years ago when CO2 was about 1,000 parts per million. So that's sort of like worst case scenario next century maybe for us. And yeah, there you would have had alligators and things somehow enduring, polar night for months on end. So this is this is a no analog biosphere that we don't even know how that ecosystem sort of works, having a rainforest in the Arctic. So yeah, totally different world. It's kind of crazy that it doesn't seem like CO2 is that much higher than like 1,000 parts per million, and that's how different the planet is. So that should hopefully, if you suddenly changed our ice age world to that in a few centuries, like I don't know what that looks like.
I realize this question should have been asked probably right at the beginning, back when we were talking about why do we care about CO2. But, again, CO2, we're looking, if we were to make it rice grains, we'd have like 4 blue rice grains for every 10,000 rice grains. And we go like, why does that make such a big difference on the climate? Honestly, it's such a tiny proportion. Water vapors, such a more potent greenhouse gas. So just kind of for dummies, walk us through again why CO2 is such a driver of these climactic swings.
I mean, that is true. Water vapor is a more powerful greenhouse gas than CO2 and does trap more heat.
Way more powerful,
right?
Yeah,
and traps more heat than CO2 does on the surface of the planet. But water vapor condenses and rains out on an average of something like 9 days. Any additional amount of CO2 you put in the air, some of it is going to stay up there essentially indefinitely. Again, some people you'll see things cherry picked where it's like, oh, well, the average residence time for CO2 is actually, not that long either, but it's constantly being exchanged with the biosphere. It's just that the additional amount that goes into the air stays up there essentially. And so water vapor acts as a feedback to CO2 because the water vapor can change very quickly, but the CO2 can't really. It just stays up there. And it also blocks out, it traps heat from a part of the spectrum that doesn't overlap very much with the others. So it is, there's this classic paper that calls it the principal knob driving or governing Earth's temperature. And it's because I think of those two things, the fact that it traps heat exceptionally well from this one part of the spectrum and that it doesn't condense and, snow out or rain out on a short time scale, unlike other things like water.
I think in the book you talk about how humanity has sort of stepped on, like we talked about the carbon cycle. In other episodes we talked about nitrogen cycle, phosphorus cycle, but the water cycle itself, it's moving faster. Can you help us understand that or quantify that, like due to increases in CO2?
Yeah, I mean, just as it gets warmer, the water cycle accelerates, basically, amplifies. So kind of a weird, super long-term, this is getting really like wacky, but the sun is slowly getting brighter over time, just as on its path as like a main sequence star. And if you project that hundreds of millions of years in the future, eventually it'll be bright enough that the water cycle will be accelerated enough that rock weathering will actually be accelerated enough that you'll draw CO2 down so far that photosynthesis can't exist and all life on Earth will end. So that could happen long before like the classic the oceans boil off, because this is like, no, the rock weathering gets too good and CO2 declines below the threshold for photosynthesis. So, but I mean, I think since the Industrial Revolution, the water cycle has accelerated like 25% or something like that. I forget the exact numbers. And it's because when you trap more heat on the surface of the planet, you can evaporate and precipitate, more water. That's just, there's more energy in the system.
And that is one of the negative feedback mechanisms to eventually draw the CO2 down, but it just may take tens of thousands of years rather than a few hundred, as we might need.
Yes. So this is kind of one of the miraculous things, along with that amazing nanomachinery I was talking about. Like one of the reasons why writing this book, I came away feeling just so grateful to be alive is that the carbon cycle can go out of control and bad stuff can happen, but for the most part, it has stayed within this astoundingly narrow window, and it's done so through these incredible negative feedbacks and this thermostat that exists, where when CO2 suddenly goes up too fast and it makes it warmer and accelerates the water cycle, it actually accelerates rock weathering too, which draws CO2 down, which then cools things off. And conversely, if CO2 seems like it's starting to fall too far and things are getting too cold, that slows down all these processes. And so then you're able to build up more in the atmosphere and keep it within this nice habitable window. The problem with that is that is sort of like those processes happen on 100 millennia timescales. And every once in a while in Earth history, you get some weird thing come along that can overwhelm, is just acting on a bigger scale, on a shorter time scale, that it just makes those sort of emergency breaks irrelevant. And then it can just sort of build up as much as it wants. And that's what you see in the big mass extinctions. And that's what, you're seeing today. And so, yeah. But again, it's cool that people are studying things like these artificial rock weathering, which totally builds off this legacy of geoscience. Like, this is what saved us after previous mass extinctions. It's kind of ironic, I guess, that we're now using it to try to save ourselves.
I was looking at this because I just got back from touring a big gold mine in Australia, and the sheer volume of rock they have to grind up, and I think with gold mining you got to grind it up to a few microns, right? And I'm like, well, if we're already spending like 4 or 5% of global primary energy grinding up rocks, maybe we could just start blowing that dust into the air. And of course, there's all bunch of horrible problems with that process in terms of all kinds of dust itself. PM 2.5 particles aren't very good for people, and toxic elements and arsenic and things like that. But yeah, definitely interesting. You mentioned, one day the sun's heat may speed up the water cycle, draw down the CO2. When CO2 kind of hit its, I forget if it's I think it's a nadir, it got to its lowest at about 180 parts per million. You argue that that may have been part of what precluded us from pursuing agriculture. Like photosynthesis just wasn't productive enough.
Yeah, so photosynthesis actually it gets more, it likes higher CO2. So this is another sort of like cherry pick thing that you'll hear where it's like, well, plants love CO2, and obviously they do. But that's kind of irrelevant to the problems that we're facing today. But yes, there is this idea that during the ice ages, CO2 was so low that things like agriculture would have been impossible. I think there's other reasons, like the climate was incredibly volatile even within the ice ages. You'd have, rafts of icebergs would get dumped in the North Atlantic and shut down the AMOC, and it was very difficult to sort of stay put for generations, like making a sedentary farming society if the next year your farm could be covered in a dust storm or the temperature could change by dramatically, and it was just a very difficult, volatile environment. And so then the Holocene, this like modern interglacial we're currently living in, has been both higher CO2, which might have encouraged it just would have helped these founder crops become easier to plant. But it's also been unbelievably and kind of eerily stable for thousands of years, and has allowed sort of these sedentary, complex societies to kind of crystallize on landscape without getting shaken up too much by the climate in the meantime. But yeah, I mean, it is, some people have pointed to the fact that a lot of the, important crops for the rise of agriculture actually is this sort of older pathway of photosynthesis that does like higher CO2. So maybe it really was constrained by just like the CO2 level in the air. And actually, it's been argued that CO2 couldn't have dropped any lower than it had, because if it had gone any lower, it might have passed that threshold for photosynthesis. And so plant life was doing a lot worse during the height of the last ice age than it is today. And there was a lot less of it, and that unused CO2 might have just like kind of stayed up in the air and helped it couldn't drop any lower because the plant, and that would be like a negative feedback, if that makes any sense.
So I think we're kind of about to leave it here, and we're going to tap into a whole other section of your book, which continues to dive into and reference the geology, but then starts to trace humanity's evolution through different sort of modes of production and into becoming not just the fire ape in terms of the obligate pyrophile of burning vast, grasslands to try and herd animals and make them run over, cliffs and whatever else, but into actual modern industrial society, and as you kind of frame it, industrial metabolism. Just one last thing I wanted to nerd out on before we kind of get into that, agriculture, then industrial revolution in the next episode. It's just this age of large mammals, which are just a kind of, for me, as much as dinosaurs are cool, I think huge sloths and, massive tapirs and things like that are pretty neat too. Is there a CO2 tie in there? You said it's the story of everything.
The only reason why we find the big mammal, like the big ice age megafauna, interesting or surprising is because we killed it all and it's not around anymore. So to us, it seems shocking that there were lions and camels in North America and these elephants in South America, and woolly rhinoceros.
Massive birds.
Well, they might check out a little before we might. Well, yeah, actually, the elephant bird in Madagascar in historical times, which had, I think, the biggest egg ever in Earth history, along with gorillas.
How big?
It was. I mean, they're huge. Along with these gorilla-sized lemurs, they all go extinct when people show up in Madagascar as well. So even into historical times, and the moa in New Zealand. So this legacy that starts, 50,000 years ago in Eurasia, and then hopscotches into the Americas, where you suddenly start, and into Australia, you suddenly start to see all the large land mammals disappear, eerily shadowing these migrations of humans, has continued into historical times as humans have continued to show up in places, which, it's tough to tell that story because these are both like heroic migrations of people making their way in these strange new continents, and it's really inspiring. But, humans are apex predators, and in those ice ages, we developed all these this incredible repertoire of technology and changing landscapes with fire and building cultures that are generational of passing on this knowledge and stuff. So it's not a surprise that when we would show up in continents where these big docile animals would have no clue that this stupid little thing that walks around on two legs is the most dangerous thing that it's ever seen in its life. And wouldn't be scared of it. And it was probably great eating for quite a while, and as humans showed up in these new places. But it's not a CO2 story insofar as the ice ages shaped the trajectory of human evolution and eventually human migration around the planet. And wherever we showed up, we had a big impact that, some people, there was this argument, when do we start the Anthropocene? Does it start in 1950 with this layer in a lake where you see evidence of an atomic weapon testing? And I think, I'm sort of a old Anthropocene person where I think, the influence of humans on the planet goes back tens of thousands of years, arguably starts with this wave of megafauna extinctions around the world.
And I guess just in closing, in terms of the start of the Anthropocene, when do we start really kind of altering the carbon cycle? We've talked before in this podcast about the Orbis spike and, the infectious disease-based deaths from the Black Plague and later from influenza and other illnesses in North America is dropping CO2. But do we start having a major impact before the Industrial Revolution? I guess it depends on what you call major, but we're starting to tip things, it sounds like, before we thought we did.
Yeah, so some people have tried to calculate just the loss of the mammoth steppe would have changed the carbon cycle in ways that might have been globally relevant, not hugely on the scale
geologic
and or the way that we have in the past couple centuries. So that it might have subtly started to change then, but then I explored this idea that it was another one of these things that sort of blew my mind about sort of the dawn and spread of agriculture all over the world. And deforestation all over the world, starting in antiquity, thousands of years ago, might have, there's this guy, William Rudiman, this University of Virginia Earth scientist, who's made this argument for a while that the carbon emissions from the rise of agriculture and human transformation of the landscape would have been changing the climate, thousands of years before the Industrial Revolution. And might have emitted something. He has a calculation in one of his papers that it was 343 gigatons of carbon just from human agriculture and land clearance. And he points to the fact that in previous interglacials, like the one we're going through now, which, like I said before, there's been dozens of advances and retreats of ice ages over the last couple million years. In previous sort of warm, brief springtimes, like the one that we've been in for the past few thousand years, it gets warm, and then as orbital things start moving sunlight around the planet, Milankovitch cycles, you start cooling again, and you get these CO2 and methane cycle feedbacks where they start declining as well, and then you're well on your way back to an ice age again. And he overlays previous ice core records of previous interglacials where you see this sudden rise, then sort of a fall. And in ours, it does that, but then it weirdly starts going up again around, I think, 7,000 to 5,000 years ago, which is right at the dawn of agriculture. And then the start of rice irrigation 5,000 years ago in China, which really takes off around 1,000 years ago all over Asia. And so we have one of the reasons why the Holocene might have been so stable is that instead of declining back into an ice age early, we've sort of artificially kept carbon in the atmosphere sort of steady.
So some very positive geoengineering.
It's this accidental
maintain and grow.
Geoengineering, which might have prevented us from going into an ice age, which is good. But as I guess we'll talk about in the next one, the alternative, which is to suddenly go the other direction by recreating this atmosphere that is we don't have any evolutionary history with, is also not good. So if we were a wise species, I think, and we have plans to exist, into geological time spans in the future, we would be wise about managing our carbon emissions and things to ward off the next ice age, but not to go so far in the other direction that it threatens us as well.
Okay, Peter, we got to leave it somewhere. Again, I tend to have guests on that I quite like and whose work I quite like, but this is I enjoyed your last book, but this one was really next level, really, really fun book. Impossible to kind of explore all the anecdotes and cool stories and narratives within even half of the book in one episode. But like the way I'm reading these days, I tend to be a little ADHD and I tend to read too quickly and not absorb as much. But now with ChatGPT at my side, I'll read, find something interesting, and then deep dive that topic. And with your book, that's made your book very slow to read because there's so many interesting little off takes. I've probably got 3 or 4 guests lined up from people that you profile
cool.
In your book. So thank you for that. You're my fixer. All around fabulous book. Looking forward to have you back to talk about part 2, which again, for those of my listeners that are familiar with Dan Jurgen's work, it has that sort of a vibe, but it ties things a lot more into sort of geography and geology. So it's a really, really nice synthesis. This one, this episode and the summary was a little bit more on the sort of deep geologic time and setting the scene. But things get really exciting as we move forward. So Peter, I will finish those last 2 chapters. It might take me a little while. But looking forward to having you back in the next few weeks and diving a bit further into this great book.
All right, great. I'm looking forward to it.
And where do people find you? Here's your opportunity for some shameless self-promo.
Peter Brannen 1 at Twitter or X or whatever you call it. And then I'm on Blue Sky, but I forget how the nomenclature goes on Blue Sky. So if you just search Peter Brannen, you'll find me on there as well.
Okay, right on. Go buy the book, everybody. Today's episode was made possible through a generous donation from the Xerxes Foundation and from listeners like you making pledges on our Substack. If you'd like to join the tribe, please do head over to our Substack, smash that pledge button, or if you would like a tax-deductible receipt, you can hit the donate button and make a contribution to our fiscal sponsor. We genuinely appreciate your support. It is only through your generosity that we are able to continue to offer energy literacy on demand.